Hello everyone, now we will discuss chapter 7, namely mixture preparation in spark ignition engines. For the mixture preparation in compression ignition engine, we will discuss it in chapter 10 along with the discussion of the combustion. This is because the mixture preparation and the combustion process in compression ignition engine is strongly coupled. This is the overview of this chapter. We'll look at the mixture requirement and then fuel metering. So we look at the gasoline direct injection. I think I also have one slide about the old fuel metering, which is carburation. So we'll take a look on the GDI and then SPI, single point injection, port fuel injection, PFI, and then fuel supply system, and the last topic we'll discuss in this chapter is liquid petroleum gas and natural gas fuel. The spark ignition engine operates by burning a premix mixture of a fuel, vapor, and air. So this is the keyword, a premix mixture, because we have non-premix mixture in compression ignition engine. So the task of the engine induction system or engine intake system plus the fuel system is to prepare such a mixture inside the cylinder from the ambient air and then fuel in the tank that satisfies the requirement of the engine over its operating regime. So as you know that the engine operates over certain range of the engine speed as well as over the range of the engine power load. So in principle, the optimum fuel air mixture ratio for spark ignition engine is that which give the required power. So it means we control the engine power with the lowest fuel consumption. Okay, this makes sense. And then consistent with a smooth and reliable operation. Okay. And then, due to the stringent requirement for the emission and so on, there is another constraint here, which is the emission. So this emission control, the constraint of this emission control may dictate a different mixture composition from this ideal and may also require a fraction of the exhaust gases to be recycled. That's why we have EGR, exhaust gas recirculation. And the purpose of having this EGR is to reduce the NOx emission. We will discuss about this one in a later chapter about the engine emission. The relative proportion of fuel and air that provides the lowest fuel consumption and then smooth, reliable operation and satisfy emission requirement at the required power level depend on engine speed and load. So we might have sometime stoichiometric mixture at other operating point. We might need to have it slightly rich, okay, to satisfy all this requirement. And then regarding the mixture composition, usually we use the parameter air-fuel ratio or fuel-air ratio plus % of EGR, okay. And then in chapter 3, I introduce you two parameters. Number one is the relative air-fuel ratio, lambda. So this is the ratio of actual air-fuel ratio to the stoichiometric air-fuel ratio, or equivalent ratio, phi. This is the ratio of the fuel, actual fuel-air ratio to the stoichiometric fuel-air ratio. And this is the formula for gamma and phi, and this is for gasoline. So gasoline has a stoichiometric air-fuel ratio of 14.6. Okay, so and you remember if phi above 1, then we have a rich mixture, below 1 is lean mixture. Lambda, if we have lambda above 1, so we have lean mixture. Lambda below 1, we have a rich mixture. This feature is showing typical mixture requirements for two operating strategies. So we have strategy A here. It is optimized or it is designed to optimize for maximum torque and then part load efficiency and idle stability. So in this one. And then strategy B here, it is optimized for emission reduction. So when you look at strategy B, the phi is hold constant at stoichiometric condition. So by having a stoichiometric mixture with phi of 1, then we can use three-way catalyst. Okay, so three-way catalyst is one of the after treatment system that can remove CO, NOx, and unburned hydrocarbons simultaneously. Okay, so three-way catalyst, they remove three emission species, three emission components, so CO, unburned hydrocarbon, and NOx. But there is a strong requirement for the effectiveness of the three-way catalyst, which is a stoichiometric mixture combustion. Therefore, for strategy B that is designed to optimize for emission reduction, it is operated under stoichiometric condition over all engine load level. So you can see there that B has a horizontal line, and this one is the load, and this one is the phi. And then A here, as I mentioned to you, it is designed for optimization of maximum torque, part load efficiency, and idle stability. So for idle condition, so its load is almost zero, so it's mean here. So in this case, we need to have a slightly rich mixture to improve idle stability. And then in chapter 6, we also take a look on the requirement to have a stable combustion at idle point, which is a minimum valve overlap. And the purpose of having this minimum valve overlap is to minimize the residual inside the cylinder chamber. Okay, and then moving to the medium load. So for strategy A, we can have a slightly lean mixture. So the purpose of this operating point is to have a better efficiency. So you know from the engine thermal efficiency dependency on the compression ratio and gamma. So when we have a higher gamma, it will have higher engine efficiency. And one of the way to have a higher gamma is by having a lean mixture. Okay, and then for the high load condition, so we need to apply an enrichment here to maximize the torque and then to prevent knocking. So I think in chapter 9 we will look at this knock phenomena. So if you have a rich mixture, then we can have a slightly slower, we can have a slightly higher laminar flame speed that can reduce the propensity to knocks. Okay, and then it can also reduce the exhaust temperature. The exhaust temperature is maximum around stoichiometric combustion condition. Okay, and then on the next chart here is showing the strategy for EGR. Okay, so A here, once again, it is designed to optimize for maximum torque and then part load efficiency and idle stability. So we have a decent EGR for medium load operating point, so somewhere here, and then no EGR, okay, for idle operating point. So this is intended to improve the combustion stability. We don't have EGR as well, so here it is for maximizing the airflow for power. So if we have less EGR, then we can have more air. So having more air allow us to have more fuel and thus have more engine power. And then for strategy B, we need to have a higher EGR. So the purpose of having higher EGR here is to reduce the NOx emission. Fuel and air distribution. So the fuel and air distribution between the cylinder is not necessarily the same. Okay, between the cylinder is not necessarily the same. It can also vary in each individual cylinder on cycle to cycle basis. So we have a variability between the cylinder, and then we have cycle to cycle variability. So sometimes people call this CCV. So cycle to cycle variability in each cylinder. Okay, and then the spread in air fuel ratio between the leanest and richest cylinders and in EGR level as well over the engine load and speed range is now carefully controlled to optimize emission control in engine catalyst system and to avoid excessive combustion variability. So with the advanced or massive research on the emission control, now we can have a good control on the variability of the engine operating condition, which consists of the cycle-to-cycle variability of the combustion, cycle-to-cycle variability of the emission, and so on. This table is showing a percentage by mass of in-cylinder unburned mixture components. So we have air, and then we have fuel, okay, and then we have residual. So residual here is the burn gas from the previous cycle, and then we have EGR to control the NOx emission. So this is the mixture composition at idle operating condition. So we don't have EGR usually, and then residual is pretty high, so 25%, okay, and then air is 70% and gasoline fuel is 5%. For the part load condition, so we have less EGR in this case, and then air is slightly higher because we have a slightly lean mixture. So for idle we have even a rich mixture, and then for the part load, to have a better engine thermal efficiency, we operate the engine under lean mixture condition. So we have more air and then less fuel. But you can see in here this 5.2 you cannot compare with this one because it is the ratio between the fuel and air, or LD fuel, that is important. Okay, so we have much increase of air compared to the increase of the fuel in here. So compared to the idle operating point, this part load condition has a leaner mixture. And then residual we have usually around 9%, and EGR is 9.2%. At the full load condition, we minimize the EGR. So in here, on this case, we have a 0% EGR, and then we have a slightly richer mixture. Okay, and then residual is usually low, so it's only 5%. Next topic about the fuel metering overview. So historically, carburetors were used to control the fuel flow into spark ignition intake manifold and distribute the fuel across the airstream. I think you can still see this carburetor in your lawn mower, and then maybe some of the old engine they still use a carburetor, but in modern engine for vehicle, this carburetor is not used anymore. So this feature is showing the schematic of the carburetor. So this is the inflow of fresh air, and then number one here is called an inlet suction, and some of this inlet suction part is connected to this component. Okay, so through this pipe number 4, so it's called pressure equalizing passage. That's number 4. And then number 2, this is a venturi throat. The principal work of this carburetor is similar to the phenomena in the nozzle diffuser. So, and then number 3, we have a float chamber, and this is the floater that will control the admittance of the fuel. So if the fuel is full, then it will close the fuel flow. But when we need to fill it something, so it means the fuel level is not full, then this float will allow the fuel entering this chamber. And then number 5, we have a calibrated orifice, so this one. And then number 6, this one is the fuel discharge tube. So this is the passage for the fuel entering this throat. Okay. And then number 7, this one is the throttle valve to control the flow of air and fuel. So the way it's worked, it is based on the pressure difference. So you can see in here that this chamber is connected to this airflow passage through pipe number 4, to the passage number 4, and then it is through also passage number 6. So the pressure from this passage number 4 is higher than the one from number 6. So there will be a force in this direction that will govern the fuel flow entering the passage number 6, and finally its exit at this point. Okay, and then at this point we have a nozzle, so it's mean there will be a reduction of the flow area. So at this nozzle zone, the airflow velocity is very high, so it is good to atomize this liquid fuel. So somewhere downstream here you have a massive fuel air mixing process, and then it's enter the engine through this passage. So and as I mentioned to you, this throttle plate will control the amount of the mixture flow. This is a simple flow control, so it's cheap, but there will be a decent pressure drop through this throttle plate, which is not good from the volumetric efficiency perspective. And then several different fuel injection concepts have been developed and used starting about 1980. This feature showing three different fuel injection system arrangement. So on the left side, it's called single point injection. So we only have one injector to serve all cylinder of the engines. And then on the middle one, we have what it's called multi-point port injection. You can also call this sometimes as port fuel injection. So we have one injector for each cylinder. Okay, so if we have 4 cylinders, then we have 4 injectors. And then the last one here, it's called direct injection. So because this is gasoline, it's called gasoline direct injection, or GDI. So each cylinder has one injector, and the fuel injection is directly inside the cylinder. So it is downstream of the intake valve. So single point injection, for sure it is simpler and then cheaper. Okay. However, there will be disadvantage in terms of the transient response. For example, if you want to change the load of the engine, so the control will govern the cylinder to change the air and then fuel flow and so on. But because the fuel introduction has some distance from the cylinder, so there will be a delay for the change of the load. And then B has a better transient response because the fuel introduction is closer to the cylinder compared to A. Okay. C will have even better transient response compared to B, because the fuel is injected directly inside the cylinder. So B and C is maybe slightly similar in terms of the complexity, but C will require a more expensive injector because it is injected inside the cylinder. We will need to have a good injector to make sure that the fuel can evaporate faster than the PFI. So in PFI, we inject the fuel upstream of the cylinder, so there'll be a time for the fuel to mix with air when entering the cylinder. But for C, once again, we need to have a good injector. So this good injector can be represented as the injector with a smaller hole size and then high injection pressure. So these two parameters means that it costs more money. So the injector is more expensive, and then the energy required to pump the fuel for C is also more, because we need to inject the fuel with higher pressure. A good thing for C, as I mentioned to you, it has a better transient response, And then later on you will see also that C will have a better fresh mixture cooling, okay, which is good from the volumetric efficiency perspective. Now let's take a look in more detail about this gasoline direct injection or GDI. This technology is ready, but the research for sure is still ongoing. So it's already go into the production line. So some of the engine has already applied this GDI technology. So GDI is being used in automobile spark ignition engine in significant volume. So in this case, we only have air or air plus EGR entering the cylinder, and then during the intake stroke and or the compression process or compression stroke, the fuel is injected using an injector located in the cylinder head into the in-cylinder air and residual gas to form a well-mixed fuel vapor, air, residual, and EGR, if any. So either it is injected during the intake stroke if you want to have a homogeneous mixture, or injected during the compression stroke if you want to have a stratified mixture. Okay, so it is in this second part. So there are two modes of operation. So fuel injection during the intake stroke. So in this case, we will have a homogeneous fuel air mixture. So before the combustion is initiated by the spark plug. Or we can set up in such a way that a stratified mixture occurs inside the cylinder chamber. So in this case, we have a stoichiometric mixture around the spark plug, and then slightly leans mixture far from the spark plug. So with this strategy, we can gain some engine thermal efficiency benefit because of the leans mixture combustion far from the spark plug. So the stratified operation, so mainly at part load condition, is designed to create a close to stoichiometric readily combustible fuel vapor air in contact with the spark plug. So the excess air in this case surround the cloud. Okay, so we have a stoichiometric around the spark plug for having a successful ignition process. So a stoichiometric mixture is very important for having a successful ignition process. And then once the flame is developed, then we can have a leans mixture ahead of the developed flame. So the engine operates a fuel lean overall, which result in more efficient engine operation. So this is the reason why we operate diesel under leans mixture condition to get the benefit of engine efficiency improvement. Stratified direct injection operation at part load is usually combined with homogeneous DI operation at higher and full load. So we have a stratified operating condition at mid-load, part load condition, and then we can change the fuel injection timing to be during the intake stroke condition to have homogeneous mixture for higher full load operating condition. And the advantage for having this strategy is inherently faster mixture preparation control during engine transient. So in this case, because the fuel is injected right into the cylinder where it will be burned. So this one is relative to PFI and SPI. So SPI, single point injection. And then the part load engine efficiency benefit from the lean operating condition when stratified. So we cannot do this with the SPI and PFI. So with the GDI, once again, we can have a stratified mixture condition during the part load condition, and thus improve the engine thermal efficiency. And what is the primary disadvantage of GDI? It is system cost. So it is the most expensive fuel metering cost compared to the other system. Next one, looking at the relevant characteristic of fuel. So fuel requirement for internal combustion engine are especially demanding. So in this case, because we have the engine combustion process that is integrated directly into the power generating operating cycle. So in this case, we have the combustion process in one system with the power generating operating cycle. So it is different from, for example, like steam power system. So the combustion system is separated from the power generating operating cycle. So the fuel characteristic impact the engine combustion, as makes sense, and emission formation processes. So the onset of any abnormal combustion phenomena, such as knock, is heavily impacted by the fuel composition, fuel properties. So you know the fuel with octane number 87, 90, 91, 96, and so on. So this fuel properties has a direct impact to the combustion performance, and in this case is the knock. So successful mixture preparation requires much more than achieving fast enough stable combustion under warm up engine condition. So the reason for that is we also need to take care the engine that is operated under cold and hot condition. So in this case, when we design the engine, we need to make sure that the engine has a good performance for cold start condition, for the hot start condition, and typically offer all available engine operating conditions. With conventional spark ignition engine liquid fuel metering system, the fuel enters the airstream as a liquid jet. It doesn't matter whether you use SPI, PFI, GDI, we will inject a liquid fuel. And then this liquid fuel will atomize into droplets that move through the air and start to vaporize. So, and then with manifold or PFI, a major fraction of this droplet deposit on the walls of the intake system component. So usually we direct the fuel injection toward the back side of the intake valve. So you will see some liquid film attached to the back side of the intake valve. So when you have SPI, so you inject it through the intake runner, so you might see some liquid film layer attached to the intake runner wall. So in this case, evaporation of the liquid fuel on the walls then occurs, and then the flow of liquid fuel along the wall can also be significant. So besides having a droplet that flow with the air stream, we might see a liquid flow along the wall. Okay, and the transport of a fuel as vapor and then droplets and liquid stream or film into the cylinder can be important. For direct fuel injection approach, the fuel spray phenomena occurs inside the cylinder of the engine, and the surrounding of this fuel spray is the charged air and the residual gas. And the residual gas is hot, and therefore the environment for this direct fuel injection is hotter, and thus increases the evaporation rate of the fuel. The evaporation of the fuel requires an energy, and this energy is taken from the charged mixture, so the mixture of air and the residual. It can be also taken from the wall heat transfer. And then the characteristic of the fuel will impact the evaporation rate of the charge. For example, the fuel of the gasoline with 85% ethanol or alcohol, so the spec name is E85, will have a higher or will require a higher evaporation energy than 100% gasoline fuel. This is because the ethanol fuel has much higher evaporation energy than the gasoline fuel. Next one is looking at a central fuel injection or SPI, single point injection. Usually this fuel injector is controlled electronically, and then the fuel is injected into the airstream, and this injector is upstream of the throttle plate. So this feature is showing the schematic of this central fuel injection system. So number one here is the pressure regulator, and this is the injector tips, and this one is the airflow, so the airflow through this one and this one. And then number four here is the supply of the fuel from the fuel tank, and this is, I think, is the fuel return. Okay, and then this one is the throttle plate. So, and the mixture will enter the engine through this passage. So you can see in here we have one injector. It is placed upstream of the throttle plate, and there will be a massive mixture of the fuel and air along this area, and it will continue also downstream of the throttle plate. So this one is a schematic from a Bosch mono G-tronic unit. And for the PFI, so port fuel injection, so PFI system required one fuel injector per cylinder, and it is also electronically controlled. The advantage of this PFI, so it can increase power and torque through improved volumetric efficiency and more uniform fuel distribution. So this advantage is compared to the SPI. And we can also have more rapid engine response to change in throttle position and more precise control of the in-cylinder air-fuel ratio. This is also relative to the SPI. Two basic approaches have been developed, so the major difference between these two is the method used to determine the airflow. So determine the airflow rate. So either it is using direct measurement, or it is estimated based on the air density and engine speed. This picture is showing the schematic of PFI. So this is the piston, and then this is the cylinder, and then 5 here I think is the injector. So this is the injector, and the airflow passage is this one. It's coming from this one. Number 7 here is the intake manifold. Yeah, this is the intake manifold, number 7. Okay, and then number 1 is the fuel tank, I think. Number 1, yes, this is fuel tank. And then we have a fuel pump, fuel filter, number 2, number 3, and then this one is might be ECU. Yes, this ECU. And then we have some sensor here, temperature sensor, and then engine speed sensor here. So temperature sensor usually is used to detect engine knock. And then 11 here in the exhaust system we have also oxygen sensor. So this is one cylinder and it has one injector, number 5, and it is placed upstream of this intake valve. This picture showing a cross section of port fuel injector. So you can see the component that make up this injector. So we have a pintle, it is at the tips, and then number 2 here is the valve needle. So this needle movement is controlled by the mechanism inside here. This needle movement control the amount of the fuel injected from this injector. So we have armature, and then spring, solenoid winding, and so on. So this port fuel injector is controlled electronically. This is an example of an event diagram showing the intake and exhaust processes along with the fuel injection pulse, and then ignition for the individual cylinders of a 4-stroke cycle 4-cylinder engine. So we have cylinder number 1, and then 2, 3, 4. First, looking at the order of the ignition. So let's start with the cylinder number 1. So we have ignition at this one, and then after the ignition of the cylinder number 1, it will go to cylinder number 3. Okay, and then cylinder number 4, and then cylinder number 2. So the ignition order will be 1, and then 3, and then 4, and then 1. Okay, so now let's take a look on each process here. For cylinder number 1, we have the ignition, which is close to top dead center firing, and then this one is the exhaust process. So you can see a different gray color level. So no color here is intake, and then slightly gray is exhaust, and then darker here is injection. So we have the exhaust process here from cylinder number 1. So this is exhaust process. And then the fuel is injected before the intake process occurs. So this is the fuel injection period. See here. And then the intake stroke process occurs right after the fuel injection process is completed. So this one. Let me put different color, purple. Okay. And this occurred the same thing for cylinder number 3, cylinder number 4, and cylinder number 2. Okay. So we have exhaust process, and then close to the end of the exhaust process, we have a fuel injection introduction into the intake system, and then the intake process occurs. It will suck in the fresh mixture consisting of air and fuel, and might be some of the EGR into the cylinder, and then compression, and then at the end we have the ignition process. So this one just showing an example of the event diagram. We might have a different event diagram depending again on the engine operating condition. So what is the engine speed and the load level.